So system designers love abstractions, but abstractions can have some hidden costs. So that's kind of the topic for today's talk. This is XL, cross-layer logging for data duplication in consensus-based storage systems. And if you have the goal to build a key value service, you might start with a library like RocksDB. So RocksDB is a persistent and crash-consistent key value store. But then you might decide you want to replicate your key value service. And a common way of doing this is to add a layer above that RocksDB key value store. So you add a replication layer, where the replication layer is responsible for replicating and ordering those commands. And then each node is going to apply commands onto its own local storage system. So we call this a layered system, but unfortunately, some of those properties that we had in the original system are now implemented twice. So disk durable consensus systems like Raft or Paxos have their own persistence and crash consistency requirements, and so does RocksDB. We can take a closer look at this problem by looking at the flow of a logical write on the leader node. So if a client sends a put command to the leader, so put key value, the first thing the leader is going to do is append that command to its own consensus log. So that's a single disk write. It's going to propagate that command to the followers. And eventually the followers, a quorum of followers are going to respond, and the command will be committed. And then committed commands get applied, which means they get written again to the storage layer. So you can see the problem that we've written the data payload V in both the consensus log and in the storage layer. And this multi-layer design is actually quite common. A brief study of other distributed storage systems like TiKV, CockroachDB, etcd, Spanner, and Cassandra all revealed a similar type of multi-layer design. So we term this problem cross-layer data duplication. Our solution to this we'll present today. First, we formulate this problem, and we'll formulate it in some detail in TiKV, which is a representative distributed key value store. And then we ask, what would a data deduplicated system look like? We'll present our practical implementation. So first, a shared library, XL, which implements an append-only log that links into storage applications like TiKV. And then TiKV XL, which is our integration of the XL library with TiKV. We'll finish with an evaluation showing that we achieve 5.5 times higher throughput on write-heavy workloads, 73% lower write amplification, all while preserving read performance and preserving the persistence and crash recovery semantics. So for the rest of the talk, first we'll look at data organization in a replicated persistent key value store and rethink that a little bit. Then we'll look at some of the high performance and practice considerations, especially how do we read data from our log and then crash recovery. We'll finish with an evaluation and brief conclusion. OK, so this is a picture of TiKV storage in TiKV. And TiKV organizes its storage into two separate LSM trees. This work doesn't actually depend on LSM trees, but that's how TiKV is written. And what TiKV does is it writes incoming Raft log entries in the Raft LSM tree. And then it writes all the applied key value data in the key value LSM tree. So what happens is when a new Raft log entry is generated, it first gets written to the write-ahead log of the Raft LSM tree. This is for crash consistency. It's persistent on disk. And immediately afterwards, it's inserted into memory for performance, so you can read it back. And this goes on for quite some time until that mem table gets full. And once it reaches a certain threshold size, the mem table is made immutable and flushed to disk to an on-disk structure called an SS table. Same 4 writes appear over on the KV side when that put command is applied. But you can see this adds up to 4 physical writes for V, so 2 write-ahead log writes and then 2 SS table writes. So is it possible for us to only write V once? We'll look at sort of an intermediate type of system. So this is a key value separated system. This isn't a new idea. So it's been explored in key value stores in WSKey, and it's also in systems like BadgerDB and Titan. And the idea here is we're going to take the values outside of our LSM tree, and we're going to store them in separate on-disk logs. These are just log files, a single file. And in the LSM tree, instead of the value, we'll store a reference to that value in the log. So that reference is just the byte offset in the log. And there's a number of benefits to doing this. So one thing you might notice, we've actually eliminated our write-ahead logs because those on-disk logs can function as write-ahead logs. But it doesn't actually solve the cross-layer duplication problem. We've still written V twice. So our solution is to merge those two logs into what we call a cross-layer log. And so step A on the raft side is just going to be to write that entry to the cross-layer log, kind of the same as in the previous two systems. But you'll notice there's no step A on the KV LSM side. So we jump right to step B, and step B is going to be to store a reference of the value V, which is in that cross-layer log. In fact, it's buried inside of that entry that we already wrote. So this introduces a new problem, which is how do we reference that payload V? How do we know exactly where V is living in our cross-layer log? So that brings us to some of the practical design challenges. So that question is going to be answered by our efficient read algorithm. We'll also talk about crash recovery. There's a lot more detail in the paper about some more detail on append-only writes, garbage collection, and range scans. This picture is a closer look at that raft entry. So it's a distributed system, which means all of these messages are sent in protobuf format. It's a wire format. And every entry has a fixed size header followed by some number of commands. So in this case, it's a few put operations. Each has their own key and value. But protobufs are not designed for random access, right? So protobufs are serialized, and they're designed for efficient transfer, not efficient random access. And so all the fields in a protobuf are encoded by variable width integers that encode the lengths of the fields in the buffer. The naive thing to do, if you wanted to read a particular field from this protobuf, is just to read the entire thing and deserialize the whole thing, and then return your value. But we can do a lot better than that. We already have to parse this entry once because we needed to apply the commands in the entry. So we're going to do a little bit more work when we parse that entry, and we're going to generate some extra code using the protobuf compiler. So for every protobuf type, the compiler generates some code. It generates a struct with a bunch of accessor methods. And then when we parse the protobuf, it populates that struct with all the data in the protobuf. We'll generate an additional getOffset method for each field in the protobuf, and we'll use that getOffset method to find the byte offset of each field in the protobuf. In the example, this raft entry is written at byte offset 10,000 in the log, but the byte offset of V1 is byte 60 within the raft entry. V1 also has a length of 4096. And then in the KV LSM tree, we're going to store a special locator, key 1, to a pair of that total offset, so 10,000 plus 60, and then the length, 4096. Then when we want to read the value associated with that key, we just do a p-read from the log using the offset and length stored in the locator. Second big challenge is how to manage crash recovery. So this is that picture we saw earlier, and we've removed all the write-ahead logging from the system. This means that the key value LSM data is only memory durable between memtable flushes. So the problem here is how can we recover key value data following a crash? In this example, we have some data stored persistently on disk. So the XL log contains 4 entries, E0 through E3. This is all persistent on disk. But the LSM trees have some data stored on disk. That would be the SS table data, and some data that's only memory durable, not backed by a write-ahead log. During a crash, we're going to lose all that memory data, and we're going to have to recover it from the XL log. You'll notice we keep a little bit of extra state persistently on disk. So in particular on the raft side, the tail pointer, which points to the end of E1, the tail points to the last persisted entry that we have on the raft side. Whereas on the key value side, we have persisted the last applied index. So the last applied entry was E0 holding KV0. We'll start with raft, replaying the log from the tail pointer through the end of the log. And that will recover all the raft entries back into memory. Then in the second phase of our crash recovery protocol, we'll start from that applied index so that we don't accidentally double apply an entry, and we'll reapply all the commands from the rest of the raft log. So that's E1, E2, E3. And that restores all the KV data to memory as well. So in our evaluation, we'll answer three major questions today. So how does writing to XL affect the end-to-end latency for consensus operations in the system? How does XL lower write amplification compared to other layered storage systems? And then just in general, how does the system perform in key value workloads? A lot more detail in the paper, including garbage collection, crash recovery, and read and write scalability. For most of our experiments, we use a 3-node raft cluster. So fast disks, NVMe disks, and fast 100 gigabit network. And we compare 3 systems. So TiKV is the baseline system. XL is our research system. And we also include XL-SO separation only, which is like that middle picture that we showed earlier, where we have 2 separate on-disk logs. So we do the key value separation, but no deduplication. Looking at the end-to-end latency of a command during the entire consensus, we measure 16 kilobyte writes and look at the median operation. And we find in XL, the median operation is much faster. Commit is a little bit faster because of KV separation makes for quicker disk operations, quicker disk writes, including from followers. But apply is dramatically faster because we're not actually doing an extra disk write on apply at all. We're just recording that locator in the KV LSM tree. This is even more apparent when we look at a CDF, not just of the median, but of the entire distribution. And apply, especially at the tail, is nearly instantaneous with XL, where it's much slower with TiKV. For write amplification, we look at several competing systems. So TiKV and CockroachDB are both systems that use 2 LSM trees, like we discussed earlier. And they exhibit 3 or 4 times rate amplification in this experiment, which is loading very small dBs. So this is only for foreground bytes. We're not even considering background compaction here. That's because they write twice to the write-ahead log and twice to the LSM tree. XL-SO, that separation only system, and etcd are a little bit different. So the separation only system removed write-ahead logging. So it shows about 2 times rate amplification. etcd has a different raft log implementation and then uses a persistent B tree for the key value information, but it also has 2 to 3 times rate amplification. Whereas TiKV XL only exhibits 1 to 2% overhead, which is almost optimal. And this is a 73% reduction versus TiKV in write amplification. Finally, we look at YCSB workloads, so a diverse set of read and write workloads. And we normalize all these results to our baseline TiKV. On the load A and F, so the write-heavy workloads, TiKV XL is up to 5.5 times faster than TiKV and also demonstrates a clear gap over the TiKV SO, the separation-only system. And then on the read-heavy workloads, TiKV XL matches performance with the separation only, showing that our read optimizations are really helping us and don't introduce any extra overhead. So in conclusion, we've talked about cross-layer data duplication. It's a pervasive cost in consensus-based storage. And we've introduced XL and TiKV XL are systems that show the benefits of eliminating data duplication in the cross-layer. One last thought to leave you with: strict data isolation between system layers. We should think about how we handle this. It can be very harmful to performance, and it's not always necessary. So thank you.